I don't do it. Hello, so we're doing CO2 transport today. I'm not gonna lie, this is my second take, and I don't like making second takes because this is all for me, selfishly. Alright, so tissue cell. Alright, so we're talking about how to get CO2 into the plasma here. So this is a capillary. This is like this whole region here is just like a capillary, and this is like a systemic cell. And so the Krebs cycle will result in the production of some CO2, and that CO2 will just diffuse out of the tissue into the capillary. And some of that CO2 will go into the plasma just through diffusion. Okay? In the same artery, in the same vein, CO2 will diffuse into the red blood cell. Alright, another way that it will get in, or another way that it will go, is that the CO2 will bind to a hemoglobin. But like not at the hemoglobin molecule, it'll bind at like a globulin, subunit. And so it's attached to the red blood cell technically, but it's not, obviously it's not in the place where the O2 will bind. And so you get a lot of CO2 will wind up here in the globulin. The most commonly tested pathway, for sure, is when CO2 reacts with water catalyzed or enacted by an enzyme called carbonic anhydrase. And carbonic anhydrase will take this water molecule and the CO2 that is diffused in, and it will start creating carbonic acid, which is H2O3C. So I wrote it really weird because I want you to actually not do it that way. Most people write it CH2O3, I think they will write it. See, I don't even know. I mean, you will see it and you'll be able to figure it out, but I think the best way is actually just to think of it in its chemical structure, which is annoying to some people. This is carbonic anhydrate. This is carbonic acid, which dissociates and becomes carbonic I think this is carbonate, bicarbonate, and a proton that it lost. So what would happen here is you'd get a huge accumulation of H+, right? But H+ actually also binds to the globulin, and you wind up actually not having that much accumulation of H+, which means you don't get a super acidic red blood cell. Another thing that's going on is you have an exchanger on the cell that's going to exchange chloride ions for bicarbonate, and you're basically just going to transport, now basically carbonic anhydrase converted, basically carbonic anhydrase made carbonic acid, but this conversion here resulted in a bicarbonate molecule that could be transported out of the cell. So carbonic acid cannot be, but bicarbonate acid can be transported outside of the cell. And this is the mass majority of plasma carbon dioxide. It's going to be this guy right here, bicarbonate, and that's going to hang out in the plasma. So so that's the moral of that story, is that that from your tissue CO2 diffuses into the cell. So I'm just going to go through this real quick, and I'm going to do it in red. Okay, tissue, then diffuse CO2 into the cell, into the plasma of the blood. It then diffuses passively in like this. Some of this passively diffused CO2 is going to react with water, and carbonic anhydrase is going to facilitate the production of carbonic acid, and that carbonic acid is going to be converted into carbonate, and carbonate is going to be exchanged for chloride. Okay, and so as a result, your loss of bicarbonate is kind of like corrected by the chloride, so your pH will remain the same, and you have this bicarbonate that is then streaming towards your kidneys and your wherever you need bicarbonate. So I know that this was an extremely low energy video, but it helped me to remember what's going on, and I hope it helped you. I'm going to start doing titles. So like, comment, subscribe. I'm going to get blood all over this diagram, okay? I'm going to get a darker blood, you know, like a gross color here. Just get this like really gross blood. Whatever, this is really morbid. This is my sign off. It's like, it's my new thing. Okay. Alright, take care everybody. Have a good day.